Hi, everybody. We're going to look at how to interpret some function notation here in the first part of chapter 1. I'm going to share my screen so that way you can see the notes presentation for today. Present. Okay, the big thing that we're going to focus on in this lecture is that this phrase of is a function of. So success is a function of planning. Is a function of is a mathematical term that really has a lot of, or a phrase that really has a lot of loaded connotation to it. So what does the phrase is a function of mean? How else could you word it? Well, I think the best way to think about that is can be changed by or is affected by. And the very first thing that we said, that success, we'll go back, success, that can be affected by the amount of planning that you put in. And the planning is what you control. That's what you directly control. And you're trying to affect the success that is the outcome. So the planning is the input and the success is the outcome. So here's another example. The number of guests G that attend your dinner party is a function of the advertised meal. That means that the outcome, the number of guests that you have at your party, is a function of the input that you put in, or your decision, what is the advertised meal. So you have some shorthand notation in math that comes up with this. G parentheses M, so G of M, that said G of M, and M represents the meal, so the input is in the parentheses. That's important, in an input in parentheses, and G is on the outside. Doesn't mean multiplication or anything like that. And then the other way people do it sometimes is G equals F of M, which G is a function of M. We don't see that as much, but we do need to be able to work with it. We use G of M a lot more. Oh, let me hide this piece here. So I just did an example here of an interpretation, G of fried chicken. So that tells me that my input, my decision was fried chicken, and my output is 17, which represents G. So that fried chicken, so that equals 17 really is what the G value is when the input is fried chicken. So it says when fried chicken is the advertised meal, 17 guests show up for the dinner party. Now, if you notice, I used when instead of, I could have used if, I guess, but I didn't use a word like for every or anything like that. I used when and if, so it's like a single circumstance. When we talk about a single input and output pair, it's a single circumstance. We're not asking for any other prediction based on that. So let's just interpret this. Let's see, G of liver and onions, and then over on the right-hand side, we have maybe what that evaluates to, G of pizza and G of filet mignon. So looking at those three different G values on the right, 25, 50, and 3, which of these inputs do you think would go to it? Well, liver and onions, I don't think a lot of people like that. So I bet you if I advertise liver and onions, I bet you I'm going to get the lowest number over here, 3. Pizza, I think 25 people will come for pizza. And filet mignon, if I let the input, if I make the decision to serve filet mignon, 50 people are going to show up, as long as they're not paying for it at least. But remember, that's that small medallion of steak that everybody likes that's very tender and very, very tasty. All right, some other examples that can kind of happen in there. After a ball is thrown, the altitude of the ball is a function of time. So what that means is that we can watch the time go and we can predict the altitude of the ball. So the time is kind of what we're controlling because it's what we're looking at, and then that will tell us what the altitude is. It's easier to measure the time. The cost to bring a group to Valley Fair is a function of the size of the group. So if we choose to bring 50 people or 100 people, that's going to change the cost to bring the group. When you pay income taxes, the tax that you owe is a function of your taxable income. So it's not really a decision in that case, but different people with different incomes, that's the input, and that tells you how much the tax they're going to have to pay. It affects the tax you have to pay. The time it takes to complete a meeting is a function of the number of issues on the agenda. Yeah, that's true. Typically, the number of issues on an agenda kind of controls or dictates the amount of time that it takes to complete the meeting. So again, outputs are the first thing listed in that phrase and inputs are the second thing. So is a function of, or could be said as, can be predicted by, can be controlled by, can be changed by, one of those three. So A is a function of B. So capital A is a function of B. So what can we do if we don't have that context with it? What do we know right away? What's it tell us? Well, it tells us that it's either going to look like this. It's going to look like A of B or A equals F of B. It also tells us that A is the output, and it tells us that B is the input. It tells us that the B is the independent variable, the ones that we can change, the decision that we make, and A is the dependent variable, which is the one that's getting the outcome. The structure of the ordered pairs. So if we list these inputs and outputs as ordered pairs, the input always comes first. So we get B, and then A of B for the second part. Or it could just simply be B comma A, and then B comma F of B, and F of B is A. So B comma A is kind of what we're looking at here, but we use this kind of extra notation sometimes to go through. So maybe we have 3 comma A of 3, and that might both take on numbers. The interpretation of A of 8 equals 50, or 50 equals F of 8. So if you kind of pair this back to the shorthand, so A of 8, so that tells us, remember, inside the input is in parentheses, so B is the input, so B is equal to 8. So when B is equal to 8, A is equal to 50. Or when B is equal to 8, A is equal to 50. See how A is right there and A is right there. So again, that's that when that's that when phrase. All right, so now let's look at kind of the example here. The amount of dog feces on the street, P, is a function of the number of dogs in a city, D. P is measured in tons per day, and D is measured in thousands of dogs. So that's kind of important. D is measured in thousands of dogs. So when D is equal to 1, we're talking about 1,000 dogs. So it says use both shorthand notations to represent the function. It says interpret 0.25 equals F of 0.1. We're going to interpret 3 comma 1. So those are those when statements. Mexico City has an estimated 2 million dogs in its federal district that produce 353 tons of poop per day. Write this fact in function notation. I think that's the last one. I gotta go back. There you go. All right, so I want you to pause the video for a second here, and I want you to see if you can come up with those 3. And then I'm gonna switch over. I'm gonna stop sharing my screen, and I'm going to go through them. So pause the video, and then we'll talk about it in a second. Okay, so we're back now. And the very first thing that we had to do is we had to say use both shorthand notations. So because it said P is a function of D, that's going to be P of D or P equals F of D. So those are the function that's the notation that we might have. Right? The next piece says interpret 0.25 equals F of 0.1. So that's this notation. So 0.25 equals F of 0.1. So now when they ask us to interpret, we're going to use a when situation. So we're going to say when. Now I don't want to say, we want to use the context here. So I don't want to say when D is equal to 0.1, P is equal to 0.25. That doesn't give us the context. So when we ask you to interpret in context, we want you to make sure that we're talking about dogs and poop here, okay? So when a city has 0.1 dogs, oh no, this was 0.1 thousand dogs. So I'm going to take 0.1 times 1,000. So that's 100, has 100 dogs. There is 0.25, and what did that 0.25 mean? Poop was measured in tons of poop per day. Right there. That's what we got. So it's, again, it's a when phrase, okay? And we had to make sure we paid attention to the units and we stayed in context. The next one is we got to interpret 3.1. So here's that part. Now we have an ordered pair, 3, 1. Well, we know that this means input, and we know that's going to be the output. So the input was D. D is thousands of dogs. So I take 3 times 1,000. So I'm going to say when a city has 3,000 dogs, there is 1 ton of poop on the street per day. Like that. Okay. The next piece was in Mexico City. We had to write this in function notation. So if I remember right, it was that last one had, oh, let me come up with it. I got to look back quick. It was 2 million dogs and 353 tons of poop. Whoa. 2 million dogs and 353 tons of poop. So I think I'm pretty good with this. I'm going to use this notation. If you want, you could have used this one, but I'm going to use, so P of, I'm going to leave that blank for now because we got to do a little work with the input. P of D equals 353 because this is the poop over here. Poop is 353, and now I need 2 million. But I need 2 million, and that has to be in thousands of dogs. So how many thousands of dogs is 2 million? Well, there's 1,000 thousands in a million. So this is 200 thousands to get to. So 2,000 thousands to get to 2 million. So there's 2,000 dogs, and they're producing 353 tons of poop. That's the way that goes. All right, we're going to go back and present. So now it's your turn to try. Okay, we're going to do section 1.1, 1.4. The volume in this is kind of just a little extra thing here. So what I'd also like you to do is take a minute and get that done in that situation to add that onto that 1 through 4. Okay, good luck on it. And if you have questions, please don't be afraid to email me, stop in and talk to me, however you want to do it, and we can chat. So thank you very much, and we will talk to you later. We'll see you in the next video.